Thanks so much. Hello, everyone, and welcome to the Efficient Elevators Manufacturers Roundtable. This roundtable is a collaborative effort between California Energy Design Assistance, also known as CEDA, and New Buildings Institute, also known as NBI. I'm Susan Harris, a Senior Technical Communications Advisor with NBI. My focus with NBI is on communications that enable tech transfer of efficiency research and guidance. I'll be your moderator today. Our goal is to bring you leaders in efficiency to answer your questions and discuss why this issue is important, where there are challenges, and how things can be better. In the week that follows, I will email links to the event recording and presentation slides. We have a panel of experts here with us today to talk about efficient elevators. Comments or questions for other attendees can be put in the chat window. And if you just hover your mouse down at the bottom of your screen, you should see chat. And then please put questions for our panelists in the Q&A section. We'll have time for questions in the end. Although during our conversations, if you have clarifying questions, please go ahead and ask, and we'll try to pause to ask those in the moment. And then any questions on different topics will probably hold to the end. We greatly appreciate the support from CEDA. And before we dive into our content, we'll hear more about this important decarbonizing program from Sean Williams, Outreach Specialist, who's here to talk with us about CEDA.
So, thank you for having me and allowing me a few moments to speak about the CEDA program, which is short for the California Energy Design Assistance Program. And it's actually the only statewide utility incentive program for new construction and major renovation projects here in California. Some of the goals of the program is to promote electrification and decarbonization. CEDA does work in collaboration with project teams to reduce energy demand, consumption, as well as carbon emissions. Through the program, we do work with and serve commercial, public, high-rise, multifamily, industrial, and also agricultural projects that are located in the Pacific Gas and Electric, Southern California Edison, SoCal Gas, or San Diego Gas and Electric service areas. So one of the 4 investor-owned utilities. Okay. Perfect. Awesome. So just a few quick points on, why one might participate in CEDA. It's a great opportunity to receive complimentary and custom decarbonization analysis that is tailored to specific project goals to help identify the most effective energy efficiency measures to implement. It's a great way to gain analysis of energy costs as well as the paybacks. Receive financial incentives to help offset the cost of decarbonization measures, and last but not least, demonstrate a commitment to high performance building practices and design. Perfect. And just want to touch a little bit on the incentives that we offer through the CEDA program. And just keep in mind, the program is completely pre-funded, completely complimentary. So there's no obligations to participate. So, if you got an eligible project, as referred to the project types earlier, and if it's in the investor-owned service, we do provide incentives. So we do offer a 2,800. This is actually, we need to update this slide. My apologies. We actually did bump up the design team incentive. It's actually a $4,000 design team incentive per project. This is a real recent change. As you can see, it is up from a $2,800 design team incentive. And this is really just goes to the design team that enrolls as a thank you for participation. Program is open to architects, engineers, owners themselves of the building. So we'd love to get that and then distributed. And then also kind of the bread and butter, we will get a free analysis and a free estimate on the measure package incentive. So speaking a little bit here about the high performance measures, kind of goes along with the theme today, high efficiency elevators. CETA aims to exceed California's decarbonization standards by identifying high performance measures and providing educational opportunities to explore use cases and best practices. This not only advances the market, but also helps qualify participants for enhanced incentives through the program. We do have a list of eligible high performance measures that can be found on the website, CaliforniaEnergyDesignAssistance.com. Okay. Perfect. And then just lastly, here's some contact information. My email's right there. So, if there's any projects that you think might be a good fit that are in design and an eligible project type, would love to chat with anybody about the program and see if their projects might be a good fit and be able to provide incentives back to the project. And I did see a question come through the chat. I think there's a portion for that later. Thank you all.
All right, thank you, Sean. Here we have a quick look at today's discussion topics. Many buildings are required to have elevators, and so we use elevators all the time. But what about their efficiency? Does it matter? The annual energy consumption of an elevator is made up of various factors. Innovations in motor efficiency, methods for reducing standby power, improvements to lighting, security, controls, and ventilation are examples of the opportunities for reducing elevator energy use by 40% or more. Today, we explore the potential for modernizing elevators and making them more efficient, including technological advancements that offer building visitors an elevated experience while also lowering energy usage and costs. I would like to now introduce you to our esteemed panelists. First, we have Harvey Sachs. Harvey is retired and, as he likes to say, still learning. He joined ACEEE in 2001 as director of the Buildings Program and is a former visiting fellow. He worked on building codes, standards, and market transformation for residential and commercial sectors, evaluating emerging technologies and energy savings programs. He co-authored the report Advancing Elevator Energy Efficiency in 2015. Jeff Montgomery with Kone is a full chain project manager at Kone with over 25 years in the vertical transportation industry. His expertise spans elevator electrification, signalization, product change management, and leadership of large multinational teams across the Americas, Saudi Arabia, and the Asia Pacific region. Craig Collins with PAE has over a decade of experience in power systems with a keen interest in advancing the integration of renewable energy. He has worked on numerous projects involving distributed generation and smart microgrid systems. Craig excels at designing robust facility systems for critical infrastructure. And with that, I would like to pass the microphone over to Harvey.
In 2015, ACEEE was approached by a leading manufacturer who felt there was need for an Energy Star program for elevators. We agreed to assemble a group of experts, review the literature, interview a lot of people, get their help, and develop a report. If you're taking notes, that was called ACEEE A1015. It seems to have been about the last consolidated effort to do this work. So given that, let's go forward. The first thing on my mind is the quiz. The elevators, the first thing on my mind before that is that the modern elevator dates to Elisha Otis's patent in 1853 for a safety elevator. To prevent falling, the Otis elevator featured a novel automatic brake that immediately stopped the car if the rope broke. Now, you'll notice that I use the rope as the term. It wasn't yet steel cables, much less anything else. And what most of you have learned to call a pulley in the industry is a shiv. So we have shivs and ropes still as the common vernacular for what most industries refer to as cables and pulleys. So that will not be on the test. I would assert that the invention of the elevator was one of the two keys to the development, utilization of the skyscraper as we know it. The other key, of course, was inexpensive structural steel. So it's a really important thing in the evolution of American cities. Despite that, the US market for new installations is only in the range of 35,000 units a year. Each one of these is a significant capital expense and will compete with other potential capital expenses. Let's go to the next slide.
Do you think this is a good time for us to see what people think about when elevators use the most energy? It looks like, wow, people were split.
Well, let's go to the next slide.
All right. And so would you like to talk a little bit about the answer, how elevators use more energy going down?
In general, they use more energy going down almost all the time. And the reason for that is that every elevator, except hydraulic ones, which we'll get to later, has a counterweight. And the counterweight weighs half as much as the maximum load of the elevator it's balancing. But as Jeff Montgomery explained, a 3,500 pound capacity elevator or 3,500 pound gross weight elevator might be rated as though 28 people could be in it, or 35 people could be in it. And Americans will not allow themselves to be packed that tightly. So almost exclusively, American elevators have less weight in them on the counterweight than in the cab. Consequently, you have to provide energy to lower the elevator. You can use that at your next cocktail party. Next. Elevators are not major energy users in American buildings. They spend a lot of time on standby. It doesn't take much energy compared to HVAC and illumination, lighting, but they're an important extension of the building lobby. And to developers, tenants, and users, the visuals matter. So a lot of money is spent on the interiors of elevators, and certainly performance in terms of smoothness and speed are important. But the easiest thing for the designing engineer is often to leave it to the code, to meet the code and don't exceed it. What we go to next, there are opportunities to reduce consumption significantly from the baseline, giving us energy and cost savings, lower carbon footprint, and in general, a much better, potentially, user experience. And I think we'll see improvements in reliability as well. So let's go on one more. Next. And in passing, just mention that low-rise elevators, 2 to 5 stops, are quite often hydraulic elevators. They use even more energy as a fraction for standby time, being ready for a passenger, than the larger elevators do. And will not be treating them. They're a declining fraction of the market. Some major manufacturers no longer even offer them. But in many cases, for low-rise buildings, it's extremely expensive to convert the elevators to modern traction elevators. So our changes have been from major changes with major energy savings potential and many other potential improvements are from DC motors to what are called gearless permanent magnet motors. And the takeaway from this slide is that those motors are much smaller and lighter. And we'll see that that allows abandoning the old penthouse on the roof of the building. We can move to things called machine room less, or MRL, elevators. And part of that is from the large sheaves needed for ropes, we're moving to various forms of flat belts, whether steel or carbon fiber. And these are driven by much smaller diameter, higher RPM sheaves. Instead of giant sheaves, which are required by the relatively large bending circles required by steel cables, belts are much more flexible. And the permanent magnet motors are happier, giving somewhat less torque at much higher RPMs. So these changes really open many, many opportunities for modern elevators, and a lot of people are taking advantage of them. The new technologies save money in part by eliminating the penthouse, as I mentioned. MRLs are machine room-less installations, much smaller controls, much smaller motors, much smaller drives, much less heat dissipation. They also offer regeneration. Instead of applying mechanical brakes that dissipate energy as heat, they can capture the energy of slowing down or braking, just like a hybrid car, to make electricity in a regenerative function to provide that power for the building or the larger grid. The next thing is that computer controls, and this is an illustration which we'll see again, of the shift from cables or ropes to flat belts. We can go ahead, we've talked about this. The next big deal is digital controls. Most of you aren't old enough to have ever had the opportunity to visit a control room full of mechanical relays that transmitted what you pushed on the button in the cab into a control that said what floor you wanted to go to. Much less having been old enough to remember operators throwing the lever to turn on and lift you to the next floor. And the modern controls are just like any other combination of chips and bright programmers. And they present many, many opportunities. And I think we'll get into those on the next slide. Standby energy will still be the best efficiency opportunity. It's relatively inexpensive, and it can dramatically cut total energy use. We're talking about a combination of things that can cut energy use in half. And one of the opportunities would be the Europeans, as in many other regulatory things, have developed standards which are useful to designers and might lead to voluntary programs in this country. One of the things that's really neat that has developed recently is the distinction between a building which has a single elevator and buildings which have multiple elevators used simultaneously. And with modern control systems, there's an enormous opportunity for things like people punching in the floor they want to go to and being directed to a particular elevator, which will make far fewer stops. It will leave as soon as it reaches a time limit or a load limit, but it'll only stop a few times to whatever height people near that have specified. And the next elevator would be serving another group. And these actually save time for users as well as energy. With that, I think I will stop because there are people who are much smarter than I am and much better at explaining. And after all, I retired and haven't done an update in the last decade. So I thank them for what they've taught me. Thanks.
Thank you so
Susan,
much.
we could go back. Sorry, we could go back one slide.
Sure can.
So if you don't mind, Harvey, I want to.
I'm not hearing anything.
Jeff, I think we lost your audio.
Jeff, please get it back quickly because you're going to know what to say. Why don't you ask him to put it in chat and you can read it.
Susan, we may have lost Jeff completely. Or Jeff, are you back? We could.
Can you hear me now?
Yeah, I think turning off your video feed might be a good approach right now so that we can hear you.
Yeah, I apologize for that. For some reason, it's been working the whole time we've been prepping, and now it just stopped. What I wanted to kind of to say, and Harvey, if you don't mind, is let's talk about energy a little bit. I think it's a piece that a lot of people don't understand where the standby comes from and where the benefits we could get and what has already been done in the industry. One of the big things is, you talked about lighting and this, the analogy of the automobile stopping. When you switch out from your fluorescent bulbs into your LED lights in the elevator, that obviously has a big impact for your energy usage. But one of the biggest things is the ability to turn them off when the elevator is not in use. Back in the day, if you wanted to, stop the energy usage in the cab, you literally had to turn off the elevator. You turned a key switch and it cut the power basically. But nowadays with the control systems and everything being computer controlled in a better manner, we're able to turn off the interior lights, turn off the fan, and then restart that very quickly. So after 5 minutes or so of the elevator standing still, you can turn off the overheads unless there's an emergency. So you do know if it's an emergency or not. And that's one of the big things, because the energy usage of an elevator, weirdly enough, it doesn't run all that much. And most of your energy is actually used during your standby time. So that's the pieces that everybody's constantly trying to figure out how to reduce is your energy efficiency. And then it gets into also with what else you have hooked up to it. I know we had talked previously about the building automation systems and the fact that with the buildings becoming more connected, that helps us to be able to judge the usage of the elevators, but it also requires that you have constant monitoring going on with your energy, constant monitoring of your elevator system, which you're running computers constantly all the time, which is also using up some portion of energy. So there's a bit of a balance in this standby between what can be done to make it as absolute energy efficient as possible compared to the usability of the building, the usability of your safety systems, your required video communication systems and things. And a lot of that is driven by code, but also by how the building's intended to be used. So it's a pretty fun topic to get into, to be honest.
Thanks, Jeff.
That kind of got me wondering. So did it used to be like a long time ago that there was a person who worked the elevator? You know, they were in the elevator to help deliver people to their floor. And did they turn lights on and off and fans on and off before we developed this technology?
Yes. You know, I obviously have not, I've seen some elevators that were built for that, but I've not actually used one that had a full attendant. But there still is the actual attendant operation in place, in use in some places, depending on what you're doing from, it's more from a security standpoint now. But oh yeah, you know, you had the guy in the middle of the car and he would take you to the next floor and he would stand there and there were stools that you could, you know, push down from the back wall of the cab so he had someplace to sit. And we do this a lot during construction use actually right now before the elevators are fully commissioned and ready for the riding public. If you're using elevators during construction time use, you have an attendant in the car and they have a little speaker box and you hit the speaker button and it says, hey, I'm at floor 4, I need to go to floor 5. And the attendant will go, yep, be there right there. He'll make the elevator drive up, stop it in the right spot, open the doors, 100% manual control. People pile in and they get off later. So yeah, it's a pretty drastic change from the way it used to be to the way it is now.
Yeah, for sure. Well, thanks for that, Jeff. And how about if we pass the microphone over to you to talk about high-rise elevators?
Yeah, absolutely. So one of the things that Harvey talked about was the permanent magnet synchronous motors and what they've done and what they've given us the ability to do. And with the higher RPMs, you can do a lot of things. A lot of elevators are no longer what they call a one-to-one rope, so you don't have a straight connection, just single pulley from counterweight to across a shiv to the car. In a lot of the low-rise units and even mid-rise units now, you have 2-to-1 roping, 4-to-1 roping, even for higher loads. So you're able to move a lot more equipment, a lot more weight in a easier manner. But every time you introduce another doubling of the number of shivs in the system, you tend to get more vibration, more noise, and things like that. So it's kind of a dream to be able to stay with that one-to-one roping with the permanent magnet motors and still move a lot of weight very fast and very high. And when you get to high-rise and ultra high-rise buildings, and we're talking, sorry for using the meters here, but I still think in meters to a lot of cases. When you're doing buildings that are over 250, 300, 400 meters worth of travel, you can't really pull, I guess, enough weight and enough speed to do what people want to do. So one of the things that has come in the industry now, this is a Kone thing, is using carbon fiber ropes, especially for the ultra high rise. They're carbon fiber ropes themselves. We call them ropes. It looks like it's a flat piece, but it's not technically a belt. And you end up having carbon fiber with an epoxy matrix over the top of it. And what this does is it allows you to use a carbon fiber and high friction coating over a shiv with a machine at the top of the hoistway. And the biggest thing with carbon fiber is it's got a very, very good strength to weight ratio, much, much better than steel. A lot more expensive, but it's significantly lighter. And anybody who rides, as Harvey said, rides bicycles knows that carbon fiber frames are a whole lot less heavy than steel frames. Anybody who watches Formula One, you don't have steel cars anymore. Everything is carbon fiber because you need that little amount of weight, but you still need an enormous amount of strength. So by using these types of rope technology, those are high rise, what you can end up doing is really reduce the weight from the system. You can go to the next slide, Susan. And this is a graph of how much weight is in the system. The bottom range is the meters of travel. And then on the left is kilograms of weight just for the rope itself. And you end up with a conventional steel rope, which you have to use for strength, especially when you get up to these taller buildings. You can see it's an exponential curve. And what ends up happening is you have to add more rope to carry the weight of the rope that you had to add to carry the weight of the rope. So it becomes completely non-viable. And then when you look at using stuff like carbon fiber and these new RUP technology, newish, you basically make that weight curve flat. So all that weight that is introduced in the system simply because of the rope weight, you end up being able to take away. At the same time, because of the way that resonance works in buildings, and if you have resonance and sway based on wind events and things, especially for high rise, it's a major concern. Steel rope resonates with buildings because it's very heavy, right? Your lighter carbon fiber things don't resonate at all. So it's very rare that you will ever have to slow an elevator down to reduce resonance. So you can maintain through wind events the same, high speed, which has the advantages of keeping the elevators running as their highest speed possible. You don't really use a ton of energy keeping it going. You have to get there and you have to slow it down. So you want it to run, full speed as much as you can with the fewest number of stops to be as most energy efficient. And then by taking all this weight out of the system, you can then, have a ton of advantages. Go to the next slide, Susan. So the biggest thing is you got smaller machine rooms, much smaller machine room loads, because your motors are smaller. You can go from a, very large motor, even though they're permanent magnet synchronous motor. If you're going to pull, a 3,500 pound elevator at, 8 meters per second, it's incredibly fast. And it's a ton of weight, and you have to spin the motors very quickly to do that. So you can just simply reduce the motor size. And by reducing motor size, it is cutting your energy usage by a significant amount. The other piece is your lower acceleration currents. And when you start talking about energy efficiency and environmental impacts, keeping your acceleration currents much lower is not only a motor issue, but it's also a cabling issue. You can use less copper in your cables. You have less loss. Less loss in the system then goes to less heat. Less heat means you don't have to have as much concentrated conditioning equipment in your machine rooms, and you have less noise. And again, less noise means you don't have to use as much material to block off said noise. So it all leads to these big benefits just by reducing weight out of the system. And when you get to the ultra high rise, this is one of the ways that you can do that. At the same time, when you look at the low rise, these same types of things at a smaller scale are in play when you start looking at reducing the weight out of the elevator cabs. Visuals are incredibly important, as Harvey has said, but the ability to use newer, more modern materials to get the same looks in an elevator while still reducing the weight has got all these same advantages all the way through the elevator chain, from low rise all the way up to the high rise. So instead of putting a 2-inch piece of wood on your wall to get a look of wood, which is what you used to do back in the day, you can now use laminates and different colors and texture materials, which are significantly lighter, which allow you to have smaller motors, less counterweight, less noise, less heat. You can see this whole thing builds. Weight is such a core component of the elevator system that it has these huge impacts when you start talking about energy efficiency throughout the entire chain. Harvey, Craig, any comments about that? I know we've talked about this before.
I would just ask one question. Do the new, stronger and lighter column ropes, belts, do they allow you to abandon the elevator change partway up on ultra high buildings? Can you get a lift of 100 stories?
Yes, that's a good question. You actually can. The tallest building, or one of the tallest buildings in the world, it's still being built, is the Jeddah Tower in Jeddah, Saudi Arabia. And it's planned to be 1 kilometer tall, so significantly taller than Burj Khalifa. And one of the things about that building is it's a quite small footprint from a building. And the desire was to be able to run an elevator not all the way to the top, but pretty close to it. So instead of having your typical rise of your elevators being 250, 300 meters, with the ultra rope and some other pieces around that, you can push that to 500, 600, 700 meters, which completely changes how you use the elevator systems. So instead of having to stop in the middle, having a transfer floor, building shafts on tops of shafts, you can do single runs from the bottom to the top. Now, that's not only just the motor technology and the rope technology and the weight was a limiting factor of that, but you also have to do some other things to the building to be able to make that a viable and useful option. Otherwise, you're just running, point to point for observation decks and things like that. This is great for. But if you want to use it for all the traffic in the building, you also have to look at dispatching pieces and making that whole system more efficient as well.
Thank you.
And Craig, were you going to say something? I saw you come off mute for a second.
Oh, actually, no, I was going to say no comment from me.
Cool. Let's go to the next slide because it actually leads directly into that. So one of the other things, and Harvey mentioned this briefly in his presentation because he knew I was going to talk about it, is how do you minimize the number of stops that an elevator takes? How do you minimize the number of elevators in a building while still getting the people where they need to be in a reasonable time frame? And that's where you start looking at these new modern dispatching systems, like destination dispatching systems. So everybody's used to walking to an elevator, seeing a button there. You can go up or you can go down. And when the elevator dings, everybody piles on and you hope there's enough room. And then you're hitting a bunch of elevators. I saw a comment in the chat that said if there's 5 people in an elevator, 6 buttons will be pushed. Yeah, pretty much. People like to hit buttons. They want to go different places. So by changing the dynamic of how the dispatching works and how the user interface works, you can really get a lot more efficiency out of your elevators. It's not only, makes it more pleasant for a user interface standpoint, but it does change how many elevators you have to have, how fast the elevators have to be, which changes, what kind of motors you have to use, how big the cars have to be, because you change how you're moving people. And depending on how much you are out and about and pay attention to buildings, obviously, as someone who's done elevators for all of my professional life, every time I walk into a building, I end up looking at the elevators and looking at how they work and their doors and everything else. But that comes from being in the industry. But you've probably seen in especially office buildings was where it started, this destination set. So instead of just putting up or down, you swipe your card or you type in the floor that you want to go to, and it tells you which elevator to actually get on. And what that does is it combines people into a grouping. If you go to the next slide, there's a fairly busy but somewhat easy way to show this. On the left-hand side, you'll see kind of your traditional dispatching system where you just have a mass of people in the lobby and everybody's pushing an up, down, down button. It dings, everybody jumps in the cars. And every car ends up serving a lot of the same floors because it's whoever happens to jump in that car and they go to floor 2 and then floor 5 and the car next to them is going to 5 and then number 6. And it's just the way it works, right? It's kind of first come, first serve, hit the buttons, and you have the elevators going up all over the place, or down, or interfloor. But on the right-hand side, you see kind of what destination dispatching does for you. You segregate the mass of people in your lobby into groups based on where they're going in the elevator or where they're going in the building. Now, obviously, this is showing a very short stack, but you can expand this and think of a 40-story building, a 50-story building. If you wanted to go to floor 44 and you had to make 7 stops to get there, you're going to be in that elevator for a long time. But if you put everybody who's going to, floor 45 to 50 in one spot, then you have the ability to go all the way up as fast as you can. And then you start slowing down, and you may make 2 stops or 3 stops instead of, making 10 stops. And the bigger the cars, the more this becomes dramatic because more people are in there going to different floors. And that, this system started really in your office space, your office segment of buildings, but it's becoming more and more common to see it. Especially we see it a lot now in residential buildings, condo buildings, in hotels are starting to see dispatching, because now that the dispatching itself is sorted and working very well, it's now into integration with other systems in the building. So if you have a high-rise residential and you have amenity floors and you end up having a party at an amenity floor, you can just put everybody who's going to that party in one elevator and they go up there, and it doesn't impact the other buildings, the other elevators in the building that people are trying to go home. So using this types of dispatching has enabled us to move into this interaction with hotels, with high-rise residential, with mixed-use spaces, with security features, where you can tag different people together based on their security codes or where they're going. There's a lot of things you can do now that we've kind of changed that dynamic from hit the button, push where you want to go and wait, to, all right, we'll tell you where to go, how to get there, and that's going to be the fastest way that the elevator will get you to where you're going. And it optimizes that for everybody else. And in a lot of cases, it allows you to have smaller elevators, or especially less elevators, to get the same amount of traffic flow. So it's really, really beneficial, especially from a usability and energy usage standpoint as well.
Jeff, thank you. That was just such a nice, clear explanation of the destination dispatching. There was a couple of quick questions in the chat I thought we might check in with you on. If someone's on the elevator and they realize they need to actually go to a different floor, how's that handled?
In destination?
Yeah, so maybe they're on floor, they change their mind about which floor they're going to.
If you are getting on the wrong elevator, or you're going to the wrong place and deciding to go somewhere else, then you wait till it stops and you get off. And you put in a different dispatching call, and it will tell you to go to a different elevator. Because the destination dispatching of how it works, there's no ability in flight to change what floor you're going to. The calls are set for that elevator specifically. So if you get on at floor 2 and you say you're going to go to floor 50 and you decide you want to go to floor 20, it's not going to stop at floor 20 unless it's already planned to be there. So you'll have to get off the elevator and then enter in a new call. This is one of the benefits of having the integration with key cards, key access cards, turnstiles, and things like that. Majority of people go to the same place all the time, especially during the rush hours and peaks of buildings. So being able to code an access card for your standard home floor and then have the ability to change that if you need to makes the journey smoother, and also helps to keep that from happening so people don't mistype things.
Thank you for that.
The improvement in average wait time and trip time, as I saw a question in the chat because it pops you up. The It kind of depends. It's kind of a hard answer, unfortunately, because it depends on the type of building. It depends on how many elevators you have. Depends on the height of the building and the speed. But you're generally going to cut 15, 20% off of your total trip time. The problem with some of that math is total trip time is not the same as waiting time. Waiting time is how long you sit in the elevator lobby. Total trip time is from when you inject a call until you get to your destination. So depending on how the building operates and how many people are putting in different floors, you can have the case where your waiting time is actually slightly longer to get into the elevator, but your overall trip time is going to be much shorter because you're not stopping 7 times. And every time you stop, you have the doors open. There's they have to wait. Then they have to close. So all that additional time is there, plus the acceleration and deceleration ramp up of your speed curves. So you're typically looking at 10, 15, 20% better overall trip time when using destination dispatching over to conventional. Sorry, I saw that in the chat and figured we'd talk about that. Let's see, there's one more slide, and this is something that also is important, and it goes to something that Harvey had talked about previously as well. So, besides this consolidating usage, which I think we talked about, destination is moving from originally a premium style into more of a standard. You're seeing it a lot more on lower rise elevators, where people are seeing the advantages that it has, not just on the ultra high rise. This same thing is occurring for a lot of these improvements in the elevator industry. Most things are brought into the industry at the high rise space. Regen drives used to be very uncommon, and they were almost always used only for high rise or ultra high rise types applications. But now regen is available pretty much down to your smallest building, smallest elevator. Now, it's true that you're not going to regen as much in a total basis, but you're probably regening more of a percentage with the low rise because you don't have as much weight in the car. So you end up having, more constant regen because you just don't have that many people in a building that's only 2 or 3 floors. Whereas if you're looking at freight cars and things like that, they can be loaded quite a bit heavier, which changes, your regen piece. So all these things that, that we've talked about, that Harvey went through, that I've talked about, are becoming more and more standard instead of premium features. And I think that's a great thing, especially in the US, because while we do have, quite a few kind of high rise and ultra high rise buildings, not nearly as many here as we do in a lot of other places around the world that I've worked in, because we have a lot more space and we typically like wider things, not, more concentrated, smaller pieces that have to go much higher. So, high rise residential is not completely common here in the US. Whereas if you go to a lot of the Asian countries or a lot of Middle East countries, everybody lives in high rise office buildings on the 25, 30, 40th floor. That's, because of how, societies work and people moving from, more and more urbanization. So that was my spiel. Barring any questions or comments from Harvey or Susan or Craig or on the chat.
Thanks so much, Jeff. Very informative and interesting presentation. I think right now we'll hand the microphone over to Craig Collins with PAE, and then we'll have more time for questions after Craig.
Thanks, Susan. My name's Craig Collins. I'm with PAE. We're a mechanical, electrical, plumbing, technology, fire protection firm. So we help architects to design high-performance buildings. And our mission statement is accelerating change through technical excellence and innovation. and inspiring our clients to achieve their highest goals, doing our best work, and sharing our knowledge. This is why we're here today. Next slide, please. So the case study that I'm going to be talking about is our living building. So this is a PAE's headquarters. We share it with NBI and other tenants. It's in downtown Portland, Oregon. I was the lead electrical engineer on the project from pretty much near its inception to completion, and still kind of working on fine tuning and commissioning, and now kind of moving into the operations and maintenance phase of the building. One of the interesting, well, I'll get to that in a future slide. So it was done by ZGF Architects. PAE did pretty much everything in the building, mechanical, plumbing wise, and electrical as well. We also had ThyssenKrupp for the elevator, and it's a 58,000 square foot building. Energy use intensity is really quite low. It's only at 19. And it's very accessible from walking, biking, and light rail. Next slide, please. It's a quick shot of the rooftop, so you can see part of the aspect of the Living Building Challenge was to attempt to have net zero energy within the building. We looked at all kinds of ways in order to integrate as much photovoltaics as we could, including on the facade of the building, but we were limited by being in the downtown historical district, and so the historical review committee did not want to see any photovoltaic technology, so we sort of had to hide it on the roof. So this photovoltaic array on the building is not quite enough for net zero energy, so we also constructed a photovoltaic array at a low-income housing project that was going up concurrently, and so under the Living Building Challenge, that was how we met net zero energy on the project basis. We're about 60 or so % net zero energy on site. Next slide, please. Oh, there it goes. A little bit about the elevator in our building, and kind of why we're talking about the PA Living Building with respect to elevators is we actually have a UPS system in our building to drive our elevator. One of the key tenets of the Living Building Challenge, which is why it's the PA Living Building, is that we were not allowed to use any combustion technology within the project. So because we're a 5-story building, we were required by code to have a emergency backup source of power for our elevator, and we could not do a conventional diesel or natural gas generator. So we had to come up with an alternate solution that would provide for the legally required standby, but without having any combustion. So some specs on our elevator, so you can get a sense of how big it is or how small it is. We just have one elevator car. It's a 3,500 pound capacity car. Just looking up the specs on it, I think it's around 12,000 pounds of total weight. The building post-COVID, we're returning to office, but not fully. So the building has about an 80 daily average occupant count. The horsepower rating of the elevators is 30. We have a 25 kVA rated UPS with 20 kilowatt hours of battery energy storage, and our elevator system uses 6,700 kilowatt hours annually. So that's not for the building, but that's just for the elevator.
Greg, would you mind reminding me of what the UPS acronym stands for?
Yeah, that's uninterruptible power system.
Great, thank you.
Yeah. Next slide. Oh, and I calculated what the energy use intensity contribution of the elevator is, and it's around 0.4, which is we also have a culture of taking the stairs. So a lot of people are encouraged to take the stairs as a way to save energy and kind of express the sort of living buildingness of the building. So we don't have an elevator that is in high demand, but it's still nice to have. I use it quite regularly at the end of the day when I've gone up and down the stairs quite a bit. But yeah, so here's a quick diagram of our system. UPS is fundamentally powered by a grid under most all cases. The building does also have a microgrid system. So if we lose the grid, we have the ability to provide full backup to the entire facility. But that backup from the microgrid, not shown here, is not code compliant for emergency power. So we had to have a dedicated appliance, and that is the UPS. That UPS serves the elevator controller. I think we have the machine roomless type of system where the controller is in the jam at the top level, so in the 5th floor. And then there's an elevator motor and shiv at the top. And we power the system fully with the UPS at all times. So if we have a momentary interruption in the grid power, or if we're testing our microgrid system, which we do pretty regularly, the occupants in the elevator or users of the elevator would not notice the switching events associated with our microgrid and would not notice a grid outage. The UPS is able to provide for 90 minutes of backup operation. And it took some doing to actually calculate what that energy quantity was. We worked closely with the elevator vendor to determine the power demand and also the energy consumption of the elevator, basically running up and down fully for a full 90-minute duration, and that's how we sized our UPS so that we would meet code. Next slide. Here's a plot of the daily energy consumption of our elevator. One of the things we have in our building is really extensive energy and other resource metering. So I was able to pull the electrical energy and power demand for the elevator. This is over one day, 1st of April. And you can see the use pattern of the elevator, and the total energy consumption over that day was 20 kilowatt hours. When you divide out that 6,700 by 365, you get right around 18 and a half. So we're generally trending around 20 kilowatt hours a day. Peak power of the UPS is 7.2 kW, which I think would be quite reduced from what the native elevator power demand is. So one of the other benefits of the UPS system is that you're actually smoothing out the grid power that would otherwise be used for the elevator. So it kind of helps to reduce the peaks, which might be beneficial for your utility and maybe beneficial for your utility bills. You can also see that we do get some use right around the start of the day. I think this was a work day, a little bit of use around lunchtime. And then when people are filing out, they tend to take the stairs down, and some people, myself included, tend to take the elevator back up. So next slide. So if you are in a situation where it may be advantageous to consider a UPS in lieu of a generator, there's some things to know. It does provide continuous power during outages, or if you have a microgrid, it can help to reduce concerns about people being stuck in an elevator momentarily during microgrid switching events. So that's been a big benefit for us. You can or determine a code compliant pathway for using a UPS for an elevator. For really large high-rise systems, I think the cost of the UPS system may be prohibitive, but some of the other technologies that Jeff and Harvey were talking about earlier in the presentation help to reduce those power demands, reduce the peak demands of the elevator, and that would make a UPS that much more cost viable, but still likely to be more expensive upfront than your generator. But the maintenance requirements of your UPS on a weekly, daily basis are greatly reduced. But there is the need to have to replace the batteries in your UPS, once every about 10 years to 15 years, depending on the usage of the system. And that's it for me.
That's very cool, Craig. It's interesting having the UPS actually be the main running. So you're more or less running power into your UPS and then out from your UPS to the elevator.
Correct. That's right. That the power plot we have is on the feeder to the elevator, but it's technically looking at the power delivery to the UPS, and then the UPS delivers the power to the elevator system.
That's very cool. I can definitely see how that could smooth everything out, and help a lot. I like the energy graphic. When I saw that, I was laughing because that looks very similar, and of course it is, to the people movement plots that I'm used to seeing.
Yeah.
In terms of number of trips taken in different times of the day, you can tell when people are going to work and when they're going to lunch, and somebody's taking a break at 10 o'clock in the morning.
Yeah, absolutely.
It's very cool.
We've had quite a few clients now request assistance for designing UPSs into their projects, mostly for low to mid-rise applications. A lot of interest in urban environments where there's not much room for generators, or there's concern about providing the space for the generator indoors. If there's not room for the generator to be placed on the exterior of a building, the space premium for generators can be quite high. So UPS might be more expensive on an equipment cost, but you can get quite compact UPS systems now with the lithium ion technology. But there are a bunch of fire safety concerns associated with lithium ion batteries as well. So I guess I would just say it's good to consult your architect and your MEP design team and your elevator vendors. If you're planning on doing a UPS backed elevator, it takes really tight coordination between all parties.
Yeah, there's a trade-off for everything in there.
Absolutely.
Very cool. Yeah, I would be interested to see if anybody has done that on a high rise. Just the sheer amount of power you end up needing for pulling very fast, very tall elevators is astronomically hard. But it would be neat as the battery technology continues to improve. This sounds like one of those things that may come in the opposite way of normal, come in from the low side and go to the high instead of coming in from the high and go to the low.
Well, thank you both so much for that information. And we can start to look now at the Q&A panel and go through some of the questions that have come in during our discussion. I'm just looking at the first one here in the Q&A, and it's asking about how to estimate energy and cost savings of elevator retrofits and implementation cost rules of thumb. Do any of you have a sense of that? Could you talk to that a little bit?
I can tell you that there is no rule of thumb, because especially when you're talking about modernization, it depends on what you're moving from and what you're moving to. If you have an old MG set that's 40 years old with a DC geared motor, and you're moving to a brand new PMSM motor with a regen drive and a new control system, those aren't even in the same realm. But with how long that we've had the PMSM motors, you can start getting, you're starting to get retrofits now, depending on the elevator system and what they want to do. It could be 10, 15 years when you want to modernize different parts of it. So if you're modernizing something which is already to those standards, you're not going to gain a ton, a little bit here and there, but not a ton. But if you're going from very far, it's a very difficult question to answer. I would say that there are tools to do that. Some of them are available on the web. I know Kone has an energy calculator that we use for answering those types of questions, but it's very much almost a case-by-case basis.
Sure, that makes sense. Shannon, did you? Sorry, I didn't mean to talk over you. Shannon, did you want to add something? It looked like perhaps you did, but maybe that was just a kind of a notice on the system there. And then the next question is asking about what are the human factors of waiting and expectation management that are part of dispatch optimization? Could you have a green car that optimizes for energy instead of user timing?
I'll take this one because this is what I've talked about. So in terms of the human factors for waiting and expectation management, it's really around the standards of the building that you use. There is a guide called the SIPSI guide, which classifies space, office space, rental space, retail space in different classifications. And part of that classification for the building itself is the waiting time and the total trip time for an elevator system. So really the two biggest pieces that you look at is how long are you waiting in the lobby? And then how long does it take you from hitting the button to getting there? Those are the two biggest things. When you talk about the actual human factors instead of the math factors of it, a lot of it is around attention and how occupied you can get your users, so you don't necessarily feel the amount of time, because time, while it's a math thing, is also quite relative for the human. So you can reduce the felt waiting time and have slower cars if you're willing to, have a lower standard. You can reduce the felt waiting time simply by having some type of engagement in the elevator lobby. That's, you see a lot of elevators now, a lot of lobbies now, which have scrolling ticker tapes in office buildings, or media being presented in the car, or media being presented outside of the car. Little commercials. It's like the gas pump when you go and you see the gas station TV. Gas station TV is there to raise revenue, but it's also to make it not quite as boring to stand there and pump gas. The same types of things are useful in the elevators to reduce the waiting time. So those are the types of the human factors that you're dealing with, but really the optimization is all about the math. How can I get a person from point A to point B in the shortest amount of time possible, taking into account any other things about them? You can change certain cards for, if someone breaks their leg and it's going to take a little bit longer, you can actually increase the time they have to get to the elevator to calculate that trip time. In terms of using dispatching more for a, optimized for energy usage, I think it's something that could be done. It's not something that I know of that is done, because that's not the standards that the buildings are around. They're not necessarily around how absolutely efficient are you at using the energy. It's about how are you moving people from point A to point B as fast and efficiently as possible. And then how much energy does it take to do that? You try to reduce. So it's coming from a quite different viewpoint. You definitely probably could do it that way. It's not that I know of in existence.
Well, just think about what people perceive as the value of their time in dollars per hour compared to the energy savings potential if there are 5 people in that car.
Mm-hmm. Absolutely.
End of rant.
Yeah, people do not like to be in elevators more than they have to be.
I always think of that scene in Elf where Elf like presses all the buttons in the elevator for the skyrise in New York. So many great movie scenes with elevators.
There are almost every spec I've seen for high-rise buildings. If there are too many more buttons pushed than is weight in the car, it just cancels them all and makes you re-push it.
Oh, all right. Smart. I'll move on to the next question if that's okay, and unless you have something more to say, Harvey.
I would just go back to the first question, that for safety reasons, there are, depending on the jurisdiction, pretty tight restrictions on what you can or cannot do with your own elevator. It's sort of like the checkouts required every flight. So just there are costs, regulatory costs, to ensure that people's lives are not in danger.
Good point, Harvey. Very,
Yeah.
very good point.
And I'll move on to the next question. Over a given 8,670 hours a year, are there certain types of buildings, times of the day, that can't dump the regen power into the building because the building panel can't absorb it and you can't export it to the grid? Are there enough wasted watt hours per year to spend money on equipment to harvest that energy?
I'll take that one. My take on that is that that condition, while possible, it would be quite rare. That the building that would have the constraint of not being able to export any energy, or only being able to export a certain amount of energy, would likely also be a building that would have photovoltaics or battery energy storage system or other types of on-site generation like we have in our living building. And we actually do have this exact constraint. The elevator for us, though, is not a concern. Generally, the building load is sufficient enough to absorb that regen power. So it's not an issue of an electrical panel not being able to handle it. That can be accommodated through the design pretty easily. The building will generally absorb all of that regen power and the grid will not see it. Now, if you had a condition like we do in our living building where the photovoltaic system is exporting and there's an upper cap on what the utility will allow us to export, and that elevator regen power would tip us over, then you would have to have some other means of controlling for that, to satisfy the utility. And in fact, in the living building, we have exactly that, which is we both have the UPS that's capable of handling the regen power, and so that UPS would absorb it first. And if the UPS was totally topped up and the regen power was to then export from the UPS back to the main panel, then we have another whole building battery system that's able to absorb that surplus regen power and also potentially that surplus photovoltaic power, because the time in which the constraint would happen with respect to the utility would be where the regen power would be concurrent with the photovoltaic power as well. Yeah.
Very cool. Thank you, Craig. I think the next question is probably for you too.
Yeah.
Do fire extraction fan / pump systems require UPS systems as well?
Yes, if you were to deploy a UPS for your elevator power and you needed to have code required emergency backup for your elevator power, then you also had the need to do smoke handling fans in your elevator shaft. Those are also required code required emergency power, and so the UPS system could also supply those systems. Now, the elevator power itself may be classified differently than the smoke handling aspects of an emergency system. And so you may have to have a transfer switch or multiple transfer switches downstream of your UPS in order to differentiate and satisfy your code, AHJ.
Thank you, Craig. And this last question, I think, is a great one to wrap up our session. What is the biggest energy efficiency opportunity that you've seen that is typically missed out in design? And that seems like a good question for all three of you.
I'll let Jeff take a crack at that first.
So for me, the biggest one specifically around the elevators for the design is honestly not taking it into account. Because it's such a low portion of the building, you don't get a lot of people that pay attention to that small amount of energy from a building standpoint. So it's just not considered. You don't consider the fact that a MRL solution that you can use instead of a machine room will be less heat. You don't take into account that a really premium, very heavy finish with true marble on the floor of your elevator makes you jump motor sizes. that to me is the biggest thing from an energy standpoint that I think is under or overlooked quite often, is how much weight matters.
Yeah, absolutely. I think I've learned a lot in putting this presentation together with this team about the options that are out there for us to reduce that energy consumption. And just to sort of parrot what Jeff was saying, is just reduce the weight of the system. And if you have the type of system that can support the machine roomless, then that's also has the knock-on benefit of not having to have a machine room to have space conditioning in. So you get the added benefit and cost savings of not having the HVAC conditioning for that machine room. And if you can deploy the regen technology, then that gives you the ability to recapture some of your energy when you are actually raising the car, which is something else I learned. I thought we were regenerating when we were lowering the car, but we're regenerating when we're lowering the counterweight. So that was a cool lesson learned from participating here.
Harvey, is
Well,
there
for me,
anything you'd like to add before we wrap up?
well, we started with shivs versus pulleys and tracing it back to agriculture and nautical. And we're finishing with lightweight, which starts with aviation and is increasingly important for automotive regulation and design as well. So everything's tied to everything else.
And we're lifelong learners.
Try to be.
All right. Well, I want to say thank you again to our panelists and subject matter experts. I also want to say thank you to Shannon Wilson for her coordination, and for Sean Williams for joining us to talk to us about the benefits of CETA. I'm Susan from New Buildings Institute. You'll see an email coming from us soon with a link to the recording and the presentation slides from today. And please stay in touch. Look forward to our next time to connect. Have a good day.
Thank you very much.